This is an experiment called the current balance, and it's designed to demonstrate how currents in parallel wires exert a force on the wire that causes the wires to move perpendicular to the direction of the current. So we have several pieces of hardware here that are needed to make all this work. And I'll show you these individually, but from left to right, as you're looking at it, there's a power supply, which provides voltage. It is a constant, roughly 14 volts DC, that comes out of this supply. That voltage is applied to go through these wires, which are actually this, you'll be able to see this in detail in a moment, but these heavy pieces of metal here. To keep that voltage from developing a very large current, there's a resistor here called a rheostat, which we'll look at closely too, but it allows us to change the resistance in the circuit and limit the current. The current flows through an ammeter, which will allow us to measure how much current it is, and then goes back through the other wire over here to the power supply. So there's actually current going in both wires. We'll see one going one way, one going the other. We can change that to determine the direction in which the forces are exerted. It's set up right now so that there'll be a repulsive force here which will cause this upper wire to move up. And then our task is to measure how much it moves, figure out how much forces are involved. And we do that by using gravity to measure a counter force, if you like, to push down on the wire so that we can see how much the effect of the currents are. In order to measure that position, we use a beam of light. So there's a helium neon laser over here. A laser beam comes up, hits a mirror here, and then reflects and hits this scale. So when this moves, and I'll just tap it, you can see the laser move up and down on the scale. So the reflection off the mirror sends the beam into a different direction. And there's some simple optics there, which is actually also part of this course, which will allow you to measure how much the angle changes. And from the angle, you can calculate how much the distance has changed between those two wires. So let's pause and look at each of these components a little more carefully. So this is the power supply. It's a pretty standard lab power supply. It develops 13.8 volts, and you might say, well, that's a weird voltage. But it's actually designed to be similar to what's produced by a lead-acid battery, like the one you would have in your car. It can deliver a pretty high current. So you can see right there on the label it says 22 amps surge, 20 amps if you just let it run constantly. We're not going to get any current near that. But if I turn it on right now, you'll see the voltage comes up, and then that's the current that we're measuring on this meter, and it registers roughly 10 amps. But that's not very accurate. We'll get a better measurement of it on the other side with a different meter. So that's what happens at this end. You take 110 or 120 volts off the line in AC. This device converts that to DC, delivers some 13 to 14 volts on these two wires, and then that voltage is applied to the wires, which develops a current. Let's look at what it's going into. So this is the central part of the experiment. Here's the lead from one side of that power supply. The lead from the other side is the wire, which is on the back over here, and it goes over to the other end down there where there's a meter, which we'll look at carefully. Comes back and comes through here. So really what's happening is that the power is delivered here and here. This is positive and that's negative. So the positive voltage goes up through here, comes up through this post, goes through that connection into this piece of metal, which is really a wire, but it's just big, across this way, down, and out, over here, back up, through here, out, and then back. So the current going this way in the top wire turns around and comes back through the bottom wire in the opposite sense. The currents are going opposed to one another in the wire. There's a little pan right there where we can put some weight, which will change where this wire is balanced. There's a weight here on this end which makes it level, and I've adjusted it so it's at a reasonable place. We could change that if we want to. And then the light from the laser bounces off this mirror and goes over to the other end where it makes a spot on the scale that we can measure. We will need to know how far it is from here to there so that we can calculate the distance knowing this change in angle. So while we're here looking at that, I'm just going to take a scale and set it across there so that you can measure that for yourself. I'll try to do this carefully without messing anything up. So you just want to make an estimate of the separation between the pivot point on the left and the wire on the right. I'll try it in a couple of different ways. Let's see if we can try this. It's a little hard to get it right down on there. Here we go. So you just take some numbers off that scale and make a measurement for yourself and move it around a little bit. You need to measure on the left and the right side to get it to work. Now it's a little harder to measure the other direction, but in case you think you need it, let's measure that as well. So just put the stick on here from one end to the other. This you probably can't see very well with the camera, so I'll read you some numbers. On the far end, it's 4 centimeters, and on the near end, it's 30. So the length of that top wire is about 26 centimeters. You might wonder about this little vein right there. So there's a piece of metal with 2 magnets on opposite sides. So there's a magnetic field that induces a current in that metal when the metal moves, and that current dampens out the oscillation. We had the same thing on the pan balance. It helps stabilize the rocking, so you can actually make a measurement after you've changed something. So in the background here is the rheostat. The voltage goes into one side, comes out the other. You notice we don't use this terminal. We use this one and that one. This one is connected to a slider which we can move back and forth. It's hot. So when I move it over here, that increases the resistance. There are more coils of wire in it. As I move it over here farther and farther, that makes the resistance higher and higher. And it changes the current, because for fixed voltage, more resistance means lower current. Now you can see the laser spot reflected off the mirror that's on the rocker arm. And at the moment I can tell you the current measures 1.5 amps. We're going to change things around, and I'll allow you'll be able to see both the spot and the meter in a moment, and then make some measurements on your own. The voltage is constant, and we've got a good bit of the meter wire So now you see the laser spot from the light that's reflected off the mirror, which is attached to the balance arm. It's moving up and down a little bit because the balance is rocking. I've just turned off the voltage. It's relaxing back to the state of no voltage here. We'll give it just a moment to settle down. The damper will cause the motion to settle. And you'll see a little rocking just from vibrations around the layer current causes it to move just a bit. But it's Settling in now roughly at 15.4 centimeters. And then I'll just turn the voltage on, we'll see what happens. Not too much of a motion. That's because I've got the resistance set pretty high. The current is only 1.6 amps. Turn it off again. Now I've got the resistance lowered considerably. I'll turn it on. And now you can see a bigger motion because there's more current and more magnetic force. So now I've moved the scale over to the far side of the room, and the 2-meter stick is resting on the table. The left end of it is back by the mirror. The right edge of the table is at 131 centimeters at this point. So we have 131 centimeters to here, and then I'll put this around and we'll measure in this direction from the bottom of the scale to the edge of the table, and that's 126.5 centimeters. So add those two numbers together, and that's the separation of the scale from the mirror. So that's the lever arm, which will show us the motion of the wires when we apply current. So I can't make the ammeter and the scale reading both visible to you easily, so what I'm going to do is set this so you can see the scale well, and then I'll just tell you what the current is. So now we have no weights on the wires, no voltage applied, no current. This is the equilibrium position, but I've moved the scale back just a bit. I'm going to add a weight to the wire so you can see when the two wires are in contact. This is really our ultimate reference point. Try to do that without jarring things too much. So now the two wires are touching. No current. And then I'll take the weight off and let it come to equilibrium again. I'm going to add the same 30 milligram weight we had before, but now we've got more distance, so it should work a little better. So I've put 30 milligrams on the pan, so the upper wire is now loaded with the force of gravity on 30 milligrams of extra mass, and causes it to go to a new equilibrium position. That was close to the maximum mass we could add without having the wires touch. So you can use this one measurement to calibrate the force. So let it settle out a little bit. We've got more distance than we had before. It should make it a better measurement for you. That's settled. That's a reasonable equilibrium position there. No current, just the extra mass. So now you can see the balance arm. There are two little weights on there. One is 10, the other is 20 milligrams that I've set on that little platform. Let's just zoom in on that. You can see it better. And that's what caused that last deflection, so we just add or subtract those by lifting them off with a pair of tweezers here. And it changes the angle at which the platform stabilizes. So that's what you're measuring by seeing the motion of the laser spot on the scale. So if we remove the mass, we're back to our equilibrium position with no extra mass loaded on it. The two wires are slightly separated. And the rheostat is set to have a fairly high resistance, so the current's going to be small. And I'll turn it on and I'll tell you what the current is. So the current is now 1.95 amps. I'll turn the current off. And reduce the resistance. So we'll have more current. And then I'll turn it back on. The current is now 2.5 amps. And again, I'll turn it off while I change the resistance. And then turning it back on again. The current is 3.25 amps. The quick way to make a reasonable measurement of the deflection is to look at the extremes of the swing and look for the midpoint in those. We don't really have to wait for it to go all the way to zero. Turn it off again. So here we go with the higher current. It's 4.71 amps. Turned it off, and I'm going to increase the current again. So there we go. This will be close to the maximum that's rated on the rheostat. We'll push a little bit over that to get you a larger deflection. So there it goes. So that's 6.5758 amps. The rheostat's rated at 6.5. So I'm not going to leave it on for long. And I'm going to give you one measurement at a higher current, which I can only leave on briefly, so it doesn't overheat. So here goes. Watch it at the highest current. We're going to make a measurement. Turned on. We have 9.3. 9.0, it's going up a little bit, 9.08, 9.09 amps right now, 9.08. It's going to change a little because as it gets hotter, it changes the resistance, so we have to be careful not to burn it out. I'm going to turn it off. So there you go, a whole set of measurements of the deflection for various currents and of deflection for a known mass at two different spacings of the scale from the mirror. So So it's pretty straightforward from this point to look at what the force is between those two wires and see if you can understand the basic physics behind this experiment. So to wrap up, just as a reminder of what we have, over at the far right, here's a scale which shows the position of a laser spot. We have a meter stick which allows us to measure the separation of the scale from a mirror on the back of the balance. We have a laser which sends a beam out to this mirror which goes over to that spot. I can block it. You can see that the block's there. It's coming off the mirror. And then we have the current balance itself, which is two parallel wires with current going in opposite directions. The current is supplied by a power supply, and the power supply delivers that current through a resistor, which is variable, so we call it a rheostat. The current is measured by this digital ammeter, which is an electronic device to measure the current flow, another part of basic physics that we don't really talk about very much here. But trust that as a measurement of the current. So the whole device together then connects physical forces to currents. And that's going to be fundamental in establishing some of the basic constants of physics. It's also one of the really fundamental experiments in electricity and magnetism.